Hello, I am Representat. I'll be presenting our work titled A Unified Framework for Compressive Video Recovery from Coded Exposure Techniques. Coded exposure photography aims at computationally reconstructing a high frame rate video from a low frame rate video. This is achieved by optically encoding the high frame rate video X into a low frame rate video Y with an exposure sequence phi. The high frame rate video is then computationally recovered using a reconstruction algorithm. We consider three popular coded exposure photography techniques. The first one is the global exposure coding technique, also popularly known as the flutter shutter. Here, all the pixels share the same exposure sequence. In the second category, each pixel has the freedom to have its own exposure sequence. Here, only a single compressed measurement is acquired per exposure of the sensor. The third category is the coded 2-bucket sensor that can acquire 2 per pixel coded measurements in a single exposure. However, the exposure sequences are constrained to be the complement of each other. We have all these different techniques that one can use for compressive video recovery. But how do we decide which to use? How much does each of the techniques provide an advantage over the others? How much is the advantage of using 2 measurements from C to B over a single measurement from pixel-wise coded? Answering all these questions requires a framework where all these techniques can be compared fairly. For this, we design a unified framework that can reconstruct video from coded exposure measurements. The figure shows the different parts of a framework which is non-iterative and incorporates a fully convolutional neural network. As the input, our framework can adapt to both single coded measurements such as flutter shutter and pixel-wise coded, as well as to coded exposure measurements such as coded 2-bucket sensor. In the first stage, we extract features from the input images, which we call the exposure-aware feature extraction stage. The next stage takes these features as input and reconstructs a video sequence. Next, we will look at our exposure-aware feature extraction stage in detail. Coded exposure techniques multiplex the temporal dimension of the signal into compressed measurements. A pseudo-inverse solution to this problem shows us that the signal can be recovered by using spatially local operations. Hence, fully connected networks that provide global connectivity are overkill, and we instead use convolutional layers. However, the convolutional layer weight should adapt to the different exposure pattern at each pixel. Such functionality is provided by the recently proposed spatially varying convolutional layer, which forms the first stage of our proposed framework. Next, we qualitatively and quantitatively compare our algorithm with various state-of-the-art algorithms and show that our framework provides state-of-the-art reconstruction results across the 3 coded exposure techniques. For the flutter shutter, we compare our algorithm with the GMM-based technique and see that our algorithm is better able to recover the video sequence. For pixel-wise exposure, we compare with GMM and a recent learning-based algorithm. We see that, on average, there is a performance gain of more than 1 dB in terms of PSNR in comparison to the state-of-the-art learning-based algorithm. For C2B, we observe a performance gain of about 1.5 dB over GMM-based technique. Next, we analyze when does C2B provide a significant advantage over pixel-wise exposure. We consider 2 different sequences, one where the majority of the pixels on the sensor see significant motion, and the other where majority of the pixels don't see significant motion. We see that in the second case, C2B provides much higher reconstruction performance and only a marginal improvement in the first case. In summary, we propose a unified learning-based framework for video recovery from coded exposure measurements. We propose a non-iterative fully convolutional model to recover the video signal from its compressed measurements. We show that a fully convolutional architecture with spatially varying weights is more suitable than fully connected networks. Our approach matches or exceeds the state-of-the-art video reconstruction algorithms for each of the sensing techniques. We also show that C2B has a significant advantage over single coded capture for large static scenes.